Hello and welcome to this quiet corner of the night. Tonight, I invite you to wander with me through a story that begins not in the depths of the cosmos, but here on Earth, with a piece of paper, a careful hand, and a mind that dared to imagine more than the eye could see. Before we step forward, I would love to know where in the world you are listening from. Are you curled up beneath a blanket, headphones on, eyes growing heavy? Or maybe sitting by a dim lamp, letting your thoughts drift as the world outside grows. Still, wherever you are, it is wonderful to know that we are connected through this shared curiosity, across oceans and continents, gathered under the same sky. If you enjoy these calm, late-night explorations, I kindly ask you to consider subscribing. Each new subscriber is not just a number, it is a bright spark, a piece of encouragement that fuels the creation of more journeys like this. To those who are already part of this constellation of listeners, thank you sincerely. You are the reason these stories continue. And just a gentle warning, I will do my best to keep this soothing, but the mystery might become so fascinating that you stay awake longer than you planned. If that happens, at least you'll drift into sleep with something new to wonder about. So let us begin. Long before rockets pierced the atmosphere, before telescopes peered into galaxies, humanity had only the naked eye, the sky, and the courage to ask, what does it all mean? For centuries, maps of the heavens were drawn as art. Constellations shaped like heroes, animals, and gods scattered across parchment and imagination. They were guides for sailors, calendars for farmers, myths for storytellers. But they were not cosmic maps in the modern sense. They were mirrors of our stories, not windows into the structure of the universe. Then, in the early 20th century, something shifted. Telescopes had grown more powerful, photography had found its place among astronomers, and science was ready for a new kind of map, one not of myth, but of measurement. Among those who rose to the challenge was a woman whose name deserves to be whispered with reverence: Henrietta Swan Leavitt. Working quietly at Harvard College Observatory, she discovered a way to measure the distance to stars using a special type of star called Cepheid variables. Their brightness pulsed with a rhythm that revealed how far away they were, like lighthouses blinking across the cosmic ocean. Her discovery was more than a calculation. It was a key, one that unlocked the door to a larger universe. With her work, astronomers could finally begin to chart not just the positions of stars, but the true scale of the cosmos. The universe was no longer a flat dome of lights above our heads. It was deep, vast, and layered with unimaginable distances. And then came a man named Edwin Hubble, who carried Leavitt's torch into the dark. Using the new tools of astronomy, he mapped the spiral nebulae, what we now call galaxies, and discovered they were not small, nearby clouds, but entire islands of stars, each as grand as our Milky Way. This was the first great cosmic map, one that changed everything. Imagine the shock. For generations, we had believed that the Milky Way was the entire universe, all there was and all there could be. And suddenly, with one map, the boundaries of existence shattered. Billions of galaxies stretched into every direction, and the human story became infinitely smaller and infinitely larger all at once. Picture yourself standing in that time, when the universe went from a single city to an endless continent overnight. The fear, the wonder, the trembling excitement. It was not just science, it was philosophy, poetry, and even spirituality. To map the cosmos was to redraw our place within it. As we begin this journey, we will trace the steps of how one map transformed science, culture, and imagination. From the quiet nights of early astronomers, to the discoveries that shook entire civilizations, to the modern maps that now stretch to the very edges of the observable universe. This is not just a story of stars and galaxies, but of human daring, the courage to look up and realize that the universe is far more vast, far more alive than we ever believed. And as we move forward, I invite you to let your mind drift with the thought, every map is more than lines on paper. It is a mirror of how we understand ourselves. The cosmic map was not only about galaxies, it was about our own hunger to know. After Hubble revealed that galaxies existed beyond the Milky Way, astronomers faced a staggering question. How do you organize infinity? It is one thing to know that billions of galaxies exist. It is another thing entirely to place them in relation to each other, to trace patterns in their distribution, and to draw meaning from that order. The earliest attempts at cosmic cartography were slow and almost meditative. Without the advantage of computers, astronomers sat for hours, plotting galaxy positions by hand, one dot at a time. Each point was a swirl of countless suns, each dot a whisper of light that had traveled millions of years just to reach us. It was not glamorous work. It required the patience of monks and the devotion of poets. But slowly, page by page, a picture began to emerge. The dots gathered into shapes. They were not scattered at random, as some might have expected, but clustered. Galaxies formed families, bound together by the invisible pull of gravity. These families became neighborhoods called clusters, and even those clusters were not alone. They themselves grouped into superclusters, immense assemblies of galaxies that stretched across hundreds of millions of light years. And then came the greatest revelation of all. As astronomers mapped deeper, they saw not only clusters, but filaments. Vast chains of galaxies threading through the universe like rivers of light. These filaments formed a cosmic web, a structure so immense and intricate that it rewrote our understanding of existence. The universe, it turned out, was not an endless scatter of galaxies. It was woven. Galaxies were not solitary islands, but beads strung along vast threads, and between those threads lay immense voids, regions of near emptiness, darker than the darkest night. Picture it, a map not of oceans and continents, but of light and silence, a pattern spanning billions of light years, galaxies stitched together by the quiet persistence of gravity. To gaze upon such a map was to feel both wonder and humility. On this scale, the Milky Way was nothing more than a small sparkle in one strand of the web, but the impact of these maps went beyond astronomy. They changed the way humanity thought about itself. If we were once the center of the universe, now we were a tiny note in a grand symphony, part of a design that stretched far beyond imagination. The cosmic map was not only a chart of galaxies, it was a mirror reflecting our place in the infinite. Every night that astronomers looked up at the stars after this discovery, the sky was no longer just a scattering of points. It was the visible skin of a hidden architecture. The constellations of myth were still there, of course, but behind them lay something even greater, the vast framework of the cosmos itself, and this realization was only the beginning. The maps raised new questions. What invisible forces hold this web together? What unseen matter shapes the filaments? Why do voids exist where they do? These questions would lead to the next chapter of discovery, the search for the mysterious ingredients of the universe, the dark matter and dark energy that still remain unsolved. For now, imagine yourself drifting quietly through this web. Filaments stretch across unimaginable distances, galaxies glowing like lanterns strung on invisible threads. You float past clusters and voids, through regions of light and silence, carried along by the same force that binds stars, planets, and your own body to the Earth. In that moment, you are part of the map itself, both observer and participant in the story of the cosmos. The more the universe revealed its shape, the more it whispered of deeper mysteries waiting beyond the reach of the telescope. Astronomers looked at their carefully plotted maps of galaxies, clusters, and filaments, and while the image was awe-inspiring, it was also incomplete. Something invisible was sculpting the design, something that did not shine, did not glow, and could not be seen even with the most powerful instruments. Without it, the great architecture of the universe would collapse, like a house of cards. With it, galaxies could form, filaments could stretch, and the cosmic web could hold together. That unseen force was named dark matter. The concept was as unsettling as it was revolutionary. For centuries, astronomy had been the science of light, stars, planets, galaxies, all things luminous. The very word astronomy means the study of celestial lights. But here was a new chapter. To understand the true map of the universe, one had to draw not only what could be seen, but also what could not. The visible galaxies were like bright beads on a necklace, but the necklace itself, the invisible string, was dark matter. It was the skeleton of the cosmos, hidden beneath the glowing skin of stars. The first hints came not from grand maps, but from the subtle motions of galaxies themselves. Astronomers noticed that stars at the edges of spiral galaxies were moving too fast. By Newton's laws, they should have been flung into space, unable to remain bound to their galaxy. Yet they remained, circling faithfully. Something unseen was holding them in place, providing the extra gravity needed to keep them tethered. That something was not the luminous matter we knew, stars, planets, dust. It had to be something else, invisible and immense. When the cosmic maps were overlaid with simulations of dark matter, the fit was perfect. The filaments, the clusters, the voids, all of it matched a hidden structure shaped by invisible mass. What we see in the night sky is only the glowing frosting. The true cake of the cosmos is dark. In fact, more than 80% of all matter in the universe belongs to this hidden category. Every dot on those early galaxy maps was not just a beacon of light, but a marker for something much larger and invisible, anchoring it in place. Imagine drawing a map of a forest at night, where you only mark the lanterns people carry. The true forest, the trees, the paths, the rivers, remains unseen, but the distribution of the lanterns hints at its shape. That is how astronomers approach the cosmic map. The galaxies were lanterns, scattered along the contours of an invisible forest. By studying their placement, scientists traced the outline of a hidden landscape. The realization was both humbling and exhilarating. Humanity had charted the cosmos for centuries, always believing that the map was of light. Now it was clear, the real map was mostly of shadow. Our place in the universe was not just within the Milky Way, not just within a filament of galaxies, but inside a vast invisible lattice woven from something we could not see or touch. This discovery changed how cosmologists thought about time as well. Dark matter was not a late arrival. It had been there from the beginning, guiding the growth of galaxies like scaffolding around a cathedral. Without it, the first stars might never have gathered, the first galaxies might never have formed, and the universe might be an empty void. Every point of light in the night sky owes its existence to this unseen foundation. But the story did not stop there. In the late 20th century, astronomers noticed another strange puzzle hidden in their maps. While dark matter explained why galaxies clumped together, something else was affecting how the universe itself expanded. Distant galaxies, when plotted on the map, showed a curious truth. The expansion of the universe was not slowing down, as everyone expected. It was speeding up. Some unknown force was stretching the cosmic map apart faster and faster, as though the paper itself were expanding beneath the ink. This mysterious influence became known as dark energy. The name is simple, but the mystery is profound. Dark energy makes up nearly 70% of the universe. Yet we do not know what it is. It is not a force like gravity or electromagnetism. It does not behave like matter, dark or visible. It is something else entirely, a pressure woven into the very fabric of space-time. And its fingerprints are visible in the maps. The filaments are not fixed. They are drifting apart, carried on the tide of expansion. The great web is stretching, slowly unraveling, its threads pulled thinner with every passing billion years. For astronomers, mapping the universe now meant not only capturing its structure, but also its history and future. Each map was a snapshot of a living, evolving organism. The cosmic web was not static. It was breathing, shifting, changing, as dark energy pushed galaxies farther apart. In time, the maps would show a lonelier universe, where distant galaxies slipped beyond visibility, carried away faster than light can reach us. Yet in this loneliness, there is poetry. To map the universe is to capture a fleeting moment in its story, knowing that the pattern will never be the same again. Each dot is a memory, each filament a record of where galaxies once danced together before drifting away. The cartographers of the cosmos are not only scientists, they are archivists of eternity, preserving the shape of existence before it changes forever. Consider what this means for us. We are creatures living in a moment of cosmic clarity. For the high night sky we see today, the maps we draw, the filaments we trace, all of these are visible only now, in this brief window of cosmic history. In billions of years, the sky will be emptier, the filaments thinner, the cosmic map rewritten by expansion. Future beings, if any remain, may not be able to see what we see. They may believe, as our ancestors once did, that the Milky Way is all there is. They may never know the true immensity of the cosmos. This makes our maps precious. They are not only guides for exploration, but also relics of a universe that is slipping away from visibility. Each chart, each simulation, each glowing image of the cosmic web is both a discovery and a farewell. We are witnesses to a pattern that will not last forever. And so the work continues. Telescopes map deeper, satellites chart the microwave background, surveys scan billions of galaxies. Each new effort adds to the grand mosaic, refining the picture, sharpening the details, capturing the hidden threads of dark matter and the quiet push of dark energy. The map grows more complex, but also more beautiful. And within its filaments and voids, we continue to search for meaning, asking whether the universe's architecture is simply physical, or whether it is also poetic, a pattern that speaks to something beyond numbers. Perhaps the greatest gift of the cosmic map is not the knowledge of where galaxies lie, but the perspective it offers. To see the structure of the universe is to step outside of oneself, to realize that every joy, every sorrow, every fleeting moment of life occurs within one thread of a vast, shimmering web. We are small, yes, but we are also part of something vast and connected, a story written in galaxies and stretched across eternity. The search for the universe's hidden architecture moved into a new era at the turn of the millennium. Hand-drawn dots on parchment had long been replaced by photographic plates, and those, in turn, had given way to digital detectors. But the true leap forward came with projects of breathtaking ambition, surveys designed not to study one galaxy at a time, but millions. If the earlier cartographers of the cosmos had been like explorers sketching coastlines, the modern era was like launching satellites to map the entire Earth from orbit. The most famous of these undertakings was the Sloan Digital Sky Survey, or SDSS. From its mountain perch in New Mexico, the Sloan telescope set out on an audacious mission to capture the three-dimensional positions of galaxies across a vast swath of the sky. Unlike earlier telescopes, which took careful aim at one target, the Sloan instrument was fitted with a special camera capable of photographing hundreds of galaxies in a single exposure. Each night, under the clear desert sky, the telescope opened its eye and recorded cosmic neighborhoods at a scale never before attempted. The result was astonishing. Instead of sparse dots, the maps filled with dense networks. Galaxy clusters emerged in greater clarity, superclusters took shape like mountain ranges, and filaments stretched across the cosmic canvas like glowing threads in a tapestry. For the first time, astronomers could zoom out far enough to see entire structures forming shapes almost like handwriting across the universe. And these were not just images, they were data, measured with exquisite precision. Each galaxy was not only a point of light, but also a record of distance, velocity, and history. Together, they formed a living atlas of the cosmos, one that could be studied, compared, and simulated with computers powerful enough to mimic billions of years of cosmic evolution. It was through these surveys that humanity first began to grasp the true scale of the cosmic web. The Sloan maps showed the great filaments with clarity, like veins of light glowing against the darkness. They also revealed the immense voids, regions so empty that they spanned hundreds of millions of light years with scarcely a single galaxy inside. To contemplate such emptiness was as profound as contemplating the structures themselves. It was as though the universe were written in both presence and absence, in light and silence. These maps brought the cosmic cartographers closer to answering questions that had lingered for decades. Why do galaxies cluster where they do? Why do voids form where they do? How exactly does dark matter sculpt these patterns? By comparing the Sloan maps with simulations of dark matter, astronomers could see that the two matched almost perfectly. The filaments visible to our eyes were simply traces of a much larger, invisible framework. It was as if the universe were a sculpture made of crystal, and we could see only the bright lights embedded within, while the structure itself remained transparent. But the implications did not stop at structure. The maps became tools for probing the expansion of the universe itself. By measuring how galaxies were distributed at vast scales, astronomers could detect subtle ripples, echoes from the early universe known as baryon acoustic oscillations. These ripples acted like fingerprints from the time when the universe was only 380,000 years old. To find them was to peer back across billions of years, connecting the cosmic map of today to the primordial sound waves of creation. Think of it like this. Imagine standing in a quiet valley where sound once echoed off the hills. The echoes have long since faded, but their patterns are still written in the arrangement of stones and trees. In the same way, the early universe's vibrations are frozen in the distribution of galaxies. The Sloan maps revealed those patterns, with stunning clarity, confirming theories of cosmology and tying the present universe to its ancient origins. And as the maps grew, so too did the sense of scale. For the average observer, even the Milky Way is beyond comprehension. But the Sloan survey showed us not only our place within one filament, but the connection of that filament to countless others, stretching across distances so immense they defy language. To look at these maps was to confront infinity not as an abstraction, but as a detailed chart, filled with points and structures that made infinity feel both real and strangely intimate. What made these achievements more profound was that they were shared widely. The Sloan data was not hidden in vaults or restricted to a few privileged astronomers. It was released to the public, allowing researchers all over the world to download slices of the universe and study them on their own computers. Students, teachers, amateur astronomers, all could hold a piece of the cosmic web in their hands. In a way, the cosmos had never been more democratic. Every release of data added new layers to the map, refining it, expanding it, turning the rough sketches of earlier centuries into a detailed atlas of the infinite. And with each refinement, the questions only deepened. If the universe is expanding faster and faster, where will these filaments lead? If dark matter defines the skeleton and dark energy stretches the canvas, what other forces remain hidden from us? The map was not an end. It was a beginning. Even now, as new surveys surpass Sloan in scale and precision, the original images remain iconic. They are reminders of a turning point in human history. The moment when we stepped from sketching local coastlines to charting the entire cosmic ocean. To gaze at those images is to feel the weight of perspective. We are both infinitesimal and immense, both a tiny point in the map and the ones holding the map itself. Perhaps that is the quiet poetry of cosmic cartography. In drawing the shape of the universe, we are also redrawing the shape of ourselves, our sense of belonging, our relationship to time, and our understanding of what it means to live in a cosmos that is both infinite and knowable. If the Sloan Digital Sky Survey gave us a sweeping atlas of galaxies, the next stage in cosmic mapping took us even further back in time, to the very blueprint of the universe itself. For while galaxies and clusters reveal the present-day structure of the cosmos, there is an older, fainter record written across the entire sky: the cosmic microwave background. This radiation, discovered by accident in 1965, is the afterglow of the Big Bang. It is the faint whisper of light released when the universe was only 380,000 years old, long before stars or galaxies had formed. For decades, astronomers knew it existed, but its details were hidden beneath noise and imprecision. To truly understand the shape and fate of the universe, they would need to map this radiation with exquisite accuracy. Enter the space observatories. Unlike ground-based telescopes, which must peer through Earth's turbulent atmosphere, satellites like the Wilkinson Microwave Anisotropy Probe, WMAP, and later the Planck mission could gaze unobstructed at the cosmic afterglow. From their vantage points far from Earth, they trace temperature variations across the sky, differences as slight as a few millionths of a degree. And in those variations lay the seeds of everything. When the first full sky maps from WMAP were released in the early 2000s, it was as if a veil had been lifted. The mottled patterns of hot and cold revealed the primordial fluctuations that would later grow into galaxies, clusters, and superclusters. These were the faint imprints of quantum ripples, stretched across the cosmos by inflation, frozen into the sky for eternity. Planck refined this vision even further. Its higher resolution and sensitivity provided the most detailed map of the cosmic microwave background ever created. From these maps, scientists could extract the universe's vital statistics, its age, its composition, its geometry. Suddenly, questions that had once seemed unanswerable could be given numbers. The universe was 13.8 billion years old. It was made of 5% ordinary matter, 27% dark matter, and 68% dark energy. It was flat, within a margin of error so slim that alternative models collapsed. These maps were not just scientific tools, they were works of art. To look at the Planck image of the universe's afterglow is to see the oldest light in existence, a fossil of creation itself. The color-coded patterns, swirling like delicate brushstrokes, are at once abstract and deeply meaningful. They are a reminder that the story of the cosmos is written not only in stars, but in the faintest traces of ancient light. And what did these maps tell us about our place in the grand design? They showed that the filaments and voids revealed by Sloan were not random accidents, but the inevitable outcome of those early ripples. The cosmic web, with all its beauty and symmetry, was foreshadowed in the faint patterns of the microwave background. It was as though the universe had sketched its future in soft pencil strokes before filling in the details with paint. But the cosmic cartographers did not stop there. With every new map came new puzzles. The CMB, for instance, contains anomalies, curious cold spots, asymmetries, and alignments that defy easy explanation. One region of the sky appears colder than models predict, a patch so unusual that some scientists have speculated it may hint at new physics, or even the imprint of another universe brushing against our own. Whether these anomalies are profound discoveries or statistical flukes remains uncertain, but they remind us that even in the most precise maps, mystery lingers. Meanwhile, new missions have set their sights on the next frontier. The European Space Agency's Euclid telescope, launched to chart dark energy and dark matter through precise mapping of galaxies, promises to extend our reach. Unlike WMAP or Planck, which looked at the afterglow of the Big Bang, Euclid focuses on the present-day universe, tracing how dark energy stretches space and accelerates cosmic expansion. Together, these surveys of the ancient past and the living present form a bridge across cosmic history. Imagine holding two maps side by side. One is the delicate imprint of the newborn universe, a faint pattern of ripples frozen in time. The other is the vast glowing web of galaxies we see today. The miracle is that the two align. The seeds in the first map grew into the structures of the second. The cartographers of the cosmos have, in effect, traced a line across 13.8 billion years, linking the dawn of time to the present night sky. This is perhaps the most humbling realization of all, that the universe is not chaos, but continuity. From the quantum whispers of its birth to the sprawling filaments of its maturity, everything follows a thread. And by mapping those threads, we are not only charting space, we are charting time itself. It is no wonder that these cosmic maps have entered the realm of philosophy as well as science. For what does it mean that we can know the age of the universe with precision to the first decimal place? What does it mean that the grand design is written into light so faint it takes satellites drifting millions of miles from Earth to perceive it? It means that the universe is knowable, but also that our knowing is part of the story. We are not separate from the map, we are one of its coordinates. And so the quest continues. With Euclid, with the upcoming Nancy Grace Roman Space Telescope, with surveys on Earth and in orbit, the map grows richer, deeper, more intricate, and with every new thread added, our own reflection becomes clearer. We are not merely charting the universe, we are finding our place within it. The Sloan surveys and the Planck satellite had painted a breathtaking picture of the cosmos in light. But light alone cannot tell the whole story. For as astonishing as those maps were, they revealed only a fraction of the universe, just the small percentage composed of ordinary matter. The vast remainder, the invisible scaffolding of reality, lay hidden. And so, the next step in cosmic cartography was to find a way to map what could not be seen: dark matter. Dark matter is one of the strangest and most enduring mysteries in modern science. It neither emits nor absorbs light. It does not shine, reflect, or cast shadows. And yet, its presence is undeniable. Galaxies spin in ways that defy the pull of visible stars alone. Clusters of galaxies remain bound despite the feebleness of gravity from their luminous components. On cosmic scales, dark matter is the glue that holds the universe together. To map the cosmos without, it would be like charting a city by its street lamps while ignoring the roads beneath. But how can one draw a map of something invisible? The answer lies in gravity itself. Though dark matter cannot be seen, it bends light. As beams of starlight pass near concentrations of dark matter, their paths curve, creating distortions in the images we receive. This effect, known as gravitational lensing, transforms the universe into a vast natural telescope. By carefully analyzing those distortions, by measuring the subtle elongations of galaxies, the arcs and halos produced by hidden masses, astronomers can reconstruct the invisible structures shaping the cosmos. This is where the cosmic map entered, its most uncanny phase. The first dark matter maps looked like ghostly overlays upon the visible universe. Filaments traced not by light, but by mass itself. Clumps and knots revealed where hidden halos surrounded galaxies. And on scales larger than clusters, vast networks emerged that matched, almost eerily, the luminous filaments already seen. The invisible map and the visible one were two versions of the same story, like a skeleton and its skin. One of the earliest triumphs of this method came from the Hubble Space Telescope. Though not designed as a surveyor, Hubble's precision vision made it ideal for detecting gravitational lensing. In iconic images like those of the Abell clusters, galaxies were seen stretched into ethereal arcs, as if the universe itself were painted on glass and warped by unseen hands. By analyzing these distortions, astronomers were able to weigh clusters and find that the vast majority of their mass was missing, hidden in dark matter. Later surveys took this further. Projects like the Canada-France-Hawaii Telescope Lensing Survey, and more recently the Dark Energy Survey, extended gravitational lensing into vast statistical studies. No longer confined to dramatic arcs, astronomers began measuring the tiny, shape distortions of millions of galaxies across huge swaths of the sky. From these measurements, they built maps showing the large-scale distribution of dark matter. These maps were revelatory. They confirmed that the cosmic web traced by galaxies was not an illusion of light, but a skeleton of mass. Every glowing filament was matched by an invisible filament of dark matter, often even larger and more intricate. Every void corresponded to a hollow in the dark matter network. It was as though astronomers had switched from studying the paint on the canvas to tracing the frame beneath. And with these new maps came new puzzles. For while the overall structure matched expectations, certain discrepancies emerged. Some regions contained more clumping than simulations predicted. Others seemed smoother than expected. These tensions, though subtle, stirred speculation. Were the properties of dark matter different than assumed? Could there be interactions beyond gravity, forces we had not yet considered? Each anomaly was a possible crack in the wall of our understanding. But perhaps the most profound effect of these maps was philosophical. To see the universe this way is to confront the strangeness of existence. 95% of the cosmos is invisible, and yet we can draw its outline. We live in a reality where the unseen outweighs the seen, where matter itself is but a faint tracer of something deeper. Our maps, once simple guides to stars and galaxies, had become mirrors of mystery, reflections of things we know exist but cannot touch. This, too, is part of the beauty of cosmic cartography. A map is not only a tool for navigation but a symbol of imagination. By charting what we cannot see, we extend our sense of what is real. Dark matter maps are a reminder that the universe is not constrained by human perception. It is vast, subtle, layered, and we are just beginning to sketch its outlines. And so the quest continues. New telescopes, such as the Vera C. Rubin Observatory, are preparing to deliver dark matter maps of unprecedented scale, surveying billions of galaxies to trace the invisible web in exquisite detail. The Euclid mission, now in orbit, will do the same from space, free from atmospheric distortions. Together, they will refine our understanding of the unseen framework of the cosmos, perhaps even pointing us toward the nature of dark matter itself. For now, we hold two maps side by side, the luminous and the invisible. Each enriches the other, and together they offer the closest thing we have to a true picture of the universe. A picture in which our Milky Way is just one filament among billions, a glowing thread tied into a fabric whose warp and weft are invisible but undeniable. And with each new release of data, with each new layer of detail, humanity steps further into the unknown. We are the mapmakers of the infinite, drawing not just what we can see, but what we cannot. In doing so, we remind ourselves of a profound truth. The universe is always larger than our eyes can grasp, and our maps will forever be sketches of wonder rather than final blueprints. By the late 20th century, cosmic cartographers had traced luminous galaxies, mapped the skeleton of dark matter, and peered back to the faint light of the Big Bang. The picture was vast and intricate, but one profound discovery was still missing. For the maps revealed not just what the universe contained, but how it was changing. And what they showed was shocking. The universe was not merely expanding, it was accelerating. Something unseen, something stranger than dark matter, was pushing the cosmos apart. Astronomers named it dark energy. The story began with measurements of distant supernovae, those brilliant stellar explosions that briefly outshine entire galaxies. Because their brightness follows predictable rules, they serve as cosmic yardsticks, allowing astronomers to measure distances across billions of light years. In the 1990s, two competing teams set out to use supernovae to determine whether the universe's expansion was slowing under the pull of gravity. The expectation was clear: galaxies should be tugged back together, expansion decelerating with time. But when the data arrived, the result was the opposite. The supernovae were dimmer than expected, farther away than predicted. The universe was not slowing down. It was speeding up. A hidden force, greater than the gravity of all matter combined, was stretching space itself. This revelation, awarded the Nobel Prize in 2011, changed the very idea of a cosmic map. For it was no longer enough to chart the positions of galaxies or the distribution of matter. The universe's future depended on how fast those galaxies were receding, how rapidly space was stretching. Cosmic mapping had become not only spatial, but dynamic, a chart not just of where things are, but where they are going. To understand dark energy, astronomers turned to large-scale surveys, measuring the universe's geometry and expansion history with precision. The Sloan Digital Sky Survey, pioneered a technique called baryon acoustic oscillations, subtle ripples in the distribution of galaxies, fossil imprints of sound waves that once rippled through the hot plasma of the early universe. These ripples provided a cosmic ruler, fixed in size since the dawn of time. By measuring their apparent scale at different epochs, scientists could track how the universe expanded. The results confirmed the acceleration. The ripples stretched more and more as space expanded faster and faster. Combined with supernova data and cosmic microwave background maps, a coherent picture emerged. Dark energy made up roughly 68% of the universe, dominating its fate. But what is dark energy? That question remains unanswered. Some propose it is a cosmological constant, an intrinsic property of space itself, as Einstein once imagined. Others suggest it could be a new dynamic field, slowly evolving over time. Still others speculate that it may signal a breakdown in our understanding of gravity at cosmic scales. Whatever the explanation, the maps told the undeniable truth. The universe is not only vast and ancient, but restless and ever accelerating. The discovery of dark, energy-infused cosmic cartography with urgency. For now, the question was not just where we are, but where we are headed. If dark energy remains constant, galaxies will recede ever faster, the cosmic web unraveling into isolation. Trillions of years from now, distant galaxies will fade beyond detection, leaving future astronomers in lonely islands of stars, unable to glimpse the greater universe we see today. If, on the other hand, dark energy grows stronger, the acceleration may tear galaxies apart, stars apart, even atoms apart, in a cataclysmic big rip. And if dark energy weakens or reverses, the universe may one day collapse back into itself, a fiery, big crunch. Cosmic maps, once seen as static, now became predictions of destiny. Each new survey refined the parameters of dark energy, tightening the leash on possible futures. The Dark Energy Survey, with its vast lensing maps of hundreds of millions of galaxies, pushed precision further. The Baryon Oscillation Spectroscopic Survey, BOSS, added depth, charting expansion across cosmic epochs. And the newest missions, Euclid in space, the Vera Rubin Observatory on Earth, are designed with dark energy as their central quarry. To hold one of these maps in your mind is to glimpse both origin and fate. On one side lies the faint pattern of primordial ripples frozen into the microwave background. On the other lies the accelerating flight of galaxies, rushing into futures unknown. The two are joined in a continuum of measurement, linking the infant cosmos to its twilight possibilities. Perhaps the most haunting element of all is this. Our maps may not only describe the universe, but shape how we imagine it. For if human beings had lived in an earlier epoch, before acceleration dominated, our maps would have told a different story. And if we live long enough into the far future, cosmic acceleration will erase galaxies from our view, making today's maps impossible to reconstruct. Our cosmic cartography is not timeless. It is a privilege of this moment in cosmic history. And so, when astronomers gather the data, when they release new plots of expansion history, when they unveil full-sky surveys with billions of galaxies, they are not just making maps, they are freezing time itself. They are preserving a record of the universe's great unfolding, one that future beings, perhaps cut off from these distant lights, will never be able to recover. Maps of dark energy are maps of impermanence. They remind us that even the universe changes, that what we see today will not last forever. But they are also maps of resilience, proof that tiny creatures on a small planet can trace the shape of forces that govern billions of light years. It is both humbling and empowering, and so the cartographers continue, eyes fixed on the accelerating frontier, knowing that with every new map, they are not only drawing the cosmos, but sketching the outlines of eternity. For decades, the great triumph of cosmic mapping had been its consistency. From the faint ripples of the cosmic microwave background to the vast filaments of galaxies, the data aligned beautifully with predictions. The universe seemed to follow the rules, and yet, buried within those same maps were whispers of something stranger, subtle patterns, alignments, and anomalies that defied expectation. The more astronomers looked, the more the cosmic map hinted at puzzles that refused to fade away. Most famous of these anomalies came to be known as the axis of evil. The name was half tongue-in-cheek, but the phenomenon was real. When scientists examined the large-scale temperature fluctuations in the cosmic microwave background, they expected randomness, hot and cold spots scattered without preference across the sky. But instead, the lowest multipole moments, representing the broadest patterns, seemed strangely aligned. Instead of random distribution, they pointed along a single axis, as though the universe itself had a preferred direction. This was unsettling, for the laws of physics suggest the cosmos should be isotropic and homogeneous, no special places, no preferred orientations. Yet here was a map of the very oldest light, suggesting otherwise. Could it be an artifact of measurement? A subtle error in the satellite? Scientists checked. First COBE, then WMAP, then Planck all confirmed it. The alignment persisted. While debates continue about whether the anomaly is statistically significant or merely a cosmic coincidence, the fact remains that our map is not as smooth as theory predicts, and the axis of evil is not alone. Other oddities haunt the cosmic microwave background. One is the cold spot, a region far larger and colder than expected, standing out like a bruise on the infant universe. Its cause remains debated. Some argue it may be a statistical fluke, a random but improbable patch. Others suggest it could be the imprint of something profound, perhaps a massive void in the distribution of matter, or even a collision with another universe in a multiverse scenario. If true, our cosmic map may contain signatures of realms beyond our own. On smaller scales too, alignments emerge. Some surveys suggest that the spins of galaxies are not entirely random, but may show faint correlations across vast distances. If confirmed, this would challenge assumptions about structure formation. Even the orientation of galaxy clusters has been studied for hidden order, as though the universe carries an imprint of directionality written into its fabric. For cartographers of the cosmos, these anomalies are both unsettling and thrilling. A good map should reveal the landscape honestly, without distortion. But if the anomalies are real, then the landscape itself may be stranger than we imagined. The cosmic map may be less a smooth globe and more a puzzle box, full of cracks that hint at hidden compartments. These mysteries invite speculation. Could the anomalies point to physics beyond the standard model of cosmology? Perhaps the universe is not perfectly flat or isotropic, but shaped by unknown processes at the dawn of time. Some theorists invoke exotic ideas, topological defects left over from cosmic phase transitions, relics of strings or textures woven into space. Others lean toward the multiverse, suggesting that our bubble of reality may have collided with another, leaving scars in the cosmic microwave background. And then there are those who urge caution. After all, maps are only as good as their makers. Cosmic surveys push the limits of detection and subtle systematics. Instrument noise, foreground contamination, statistical bias can masquerade as anomalies. The cold spot may simply be chance. The alignments may dissolve with new data. It is possible the universe is no stranger than we thought, and our minds are simply pattern-seeking. But even skepticism has its limits. The persistence of these anomalies, across decades, confirmed by independent instruments, ensures they cannot be dismissed outright. They remain thorns in the side of cosmology, gentle reminders that our picture is incomplete. What does it mean, then, to live in a universe with possible scars and alignments? It means that maps are not finished products, but evolving documents. Just as ancient sailors refined their charts with each voyage, astronomers refine theirs with every new satellite and survey. The anomalies may one day vanish into noise, or they may explode into revelation, forcing us to redraw our cosmic maps from scratch. In the meantime, they serve as sources of wonder. For there is beauty in imperfection, in the notion that the universe may contain asymmetries we do not yet understand. They make the maps more human, more alive, Not sterile grids of data, but stories waiting to be told. One might even argue that without anomalies, science would stagnate. Maps without mysteries are merely records. Maps with anomalies are invitations. They beckon us to question, to explore, to imagine. So, as we stare at the axis of evil, the cold spot, and the strange alignments of galaxies, we might take them less as errors and more as opportunities. Perhaps they are the universe's way of whispering, the story is not over. The map is not complete. Keep going. And in that whisper lies the essence of exploration. For the map that changed everything is not a static relic, but a living canvas, filled with lines we cannot yet explain, pointing toward futures we have not yet conceived. Anomalies are not just curiosities, they are seeds of revolution. For every time the cosmic map revealed a crack, a strange alignment, a cold patch, an unexplained correlation, scientists were forced to ask, what if our framework itself is incomplete? The standard model of cosmology, built on dark matter, dark energy, and Einstein's equations, explained much. But could it explain everything? Perhaps not. The cold spot, the axis of evil, and other deviations were unsettling reminders that the universe is more complex than neat equations. And so, in the early years of the 21st century, theorists began to push harder on the boundaries of understanding. If the anomalies were real, they might demand new physics. If the expansion of the universe was accelerating, perhaps gravity itself was misbehaving on cosmic scales. Modified gravity was one such frontier. Einstein's general relativity had reigned supreme for over a century, passing every test from solar system orbits to the warping of space-time around black holes. But what if, across billions of light years, gravity behaved differently? Some models proposed that the cosmic acceleration we attribute to dark energy might instead be an illusion, the result of gravity weakening or strengthening in unexpected ways. Theories such as FR gravity, scalar tensor models, and brain-world cosmologies gained traction, each attempting to weave anomalies into a coherent fabric. The cosmic maps became proving grounds for these ideas. By charting the growth of structure, how galaxies clustered, how voids expanded, astronomers tested whether Einstein's laws held true on the grandest scales. If modified gravity were real, the maps would reveal it in the details. Galaxy flows moving too quickly, voids expanding too wide, or lensing arcs bending light differently than predicted. Parallel to modified gravity, another radical idea gained: momentum. Perhaps the anomalies were fingerprints of a multiverse. If our bubble of space-time had collided with another in its infancy, the scars could persist as cold spots or strange alignments in the cosmic microwave background. The maps, in this view, were not just charts of our universe, but windows onto others. Though speculative, the allure of this possibility captured imaginations far beyond academia, spilling into culture, philosophy, even art. Others suggested that the anomalies might arise from exotic relics, cosmic strings, invisible filaments, stretching across space, survivors from the universe's earliest moments. These hypothetical defects, predicted by some theories of high-energy physics, could warp space-time, leaving distinct imprints in cosmic maps. To find such a signature would be to glimpse physics at energies far beyond any laboratory. Skeptics, of course, raised a different possibility, that anomalies were nothing more than noise. In a universe this vast, rare fluctuations are inevitable. Perhaps we were chasing phantoms. Yet even skeptics agreed on one point: only better maps could decide. And so the race continued, not only to gather more galaxies, more supernovae, more precision, but to stretch cartography into new dimensions. Surveys like the Dark Energy Spectroscopic Instrument, DESI, began mapping millions of galaxies in exquisite detail, measuring redshifts with unprecedented precision. The Vera Rubin Observatory promised to scan the entire southern sky repeatedly, creating a dynamic map that would reveal changes over time. Euclid launched into orbit, turned its eyes to the cosmic web, seeking distortions in galaxy shapes caused by weak lensing. Together, these projects sought to test the very foundations of cosmology, and what they found was both reassuring and troubling. On the one hand, much of Einstein's framework remained intact. The universe expanded, galaxies clustered, light bent, all broadly as predicted. On the other hand, subtle tensions emerged. Measurements of the Hubble constant, the rate of cosmic expansion today, clashed depending on whether they were inferred from the cosmic microwave background or measured from local galaxies. This Hubble tension became one of the most pressing puzzles of modern cosmology. Perhaps then, the anomalies were not isolated curiosities, but part of a deeper pattern. Perhaps they hinted that our cosmic map, though grand, was incomplete. The idea that maps could drive theory is not new. In the age of exploration, when sailors encountered lands not on their charts, the maps forced kingdoms to redraw their worldview. Similarly, in cosmology, each new survey redraws the universe. And each redraw invites radical questions. What if dark energy is not constant? What if gravity itself evolves? What if our cosmos is one bubble among many? For the dreamers, this is exhilarating. To hold a cosmic map today is to hold the possibility of rewriting physics tomorrow. To trace the faint scars in the microwave background is to imagine universes beyond sight. To test gravity with galaxies is to stretch Einstein's equations across billions of light years. And for all the caution and skepticism, one truth remains. The anomalies persist. They may fade with better data, or they may sharpen into revelations. Either way, the maps ensure that no idea, however bold, can be dismissed outright. As the telescopes stare deeper, as surveys release terabytes of data, as maps grow ever more intricate, we are reminded that the greatest revolutions often begin not with answers, but with questions. And anomalies, those stubborn scars and alignments, are the universe's way of asking. The cosmic map that changed everything is still changing. It is not a finished chart, but a living frontier. And for those willing to read between its lines, it whispers of new physics, new realities, and perhaps even new worlds. For much of the 20th century, one number defined the great cosmic quest: the Hubble constant. This deceptively simple value measures how fast the universe is expanding today. It tells us how quickly galaxies recede, how long the universe has existed, and even hints at its fate. To pin it down was to anchor cosmology itself, and for decades, it seemed progress was steady. Astronomers refined their tools, from Cepheid variable stars to Type Ia supernovae, building what came to be called the cosmic distance ladder. At the same time, cosmologists used maps of the cosmic microwave background, the faint radiation, left from the Big Bang to predict the Hubble constant indirectly. Both methods, they believed, would converge on the same value. But they did not. Instead, the universe threw a curveball. The two measurements disagreed, and not by a trivial margin, but by an amount too large to dismiss as error. This clash came to be known as the Hubble tension, and it has become one of the defining crises of modern cosmology. When the Planck satellite mapped the cosmic microwave background in exquisite detail, it gave a Hubble constant of about 67 kilometers per second per megaparsec. That means for every 3.26 million light years, galaxies recede 67 kilometers per second faster. It was a precise and elegant result, fitting beautifully within the standard cosmological model. Yet when teams on Earth measured Cepheids and supernovae in nearby galaxies, they consistently found a higher value, around 73 kilometers per second per megaparsec. The difference may not sound dramatic, but in cosmology, it was enormous. It was not merely a matter of rounding. It implied a contradiction at the heart of the cosmic map. Could the universe be playing tricks on us? Perhaps the distance ladder was flawed, riddled with subtle biases. Cepheids are bright but finicky, their brightness influenced by metallicity and environment. Supernovae, though standardized, are not perfectly uniform. But despite relentless scrutiny, the higher local measurements endured. On the other side, perhaps the cosmic microwave background analysis was missing something. Planck's results assumed the standard model of cosmology, including a fixed form of dark energy and specific values for particle physics parameters. If the real universe deviated from these assumptions, then the prediction of 67 might be off. Still, the fit was so good that few dared abandon it lightly. Thus, the tension deepened. Some physicists suggested bold solutions. Maybe dark energy is not constant, but evolves with time, altering the expansion history. Maybe new particles, dark radiation, sterile neutrinos, contributed in the early universe. Perhaps even modifications to gravity itself were required. Others whispered about unknown systematics, conspiracies of measurement we had not yet identified. What made the Hubble tension especially haunting was that it was not a fringe phenomenon. Both methods were robust, led by world-class teams using independent instruments, and both results came with shrinking error bars. The more precise the measurements became, the worse the contradiction grew. The cosmic map seemed to split in two, offering parallel realities that refused to reconcile. The implications reached far beyond a number. If the higher value was correct, then the universe was younger than predicted by the cosmic microwave background. Galaxies would have had less time to form and evolve. Dark energy's behavior might be more exotic than imagined. If the lower value was right, then our local universe might be misleading us, shaped by unknown dynamics. Either way, the crisis cut to the core of cosmology's confidence. This was not the first time maps betrayed expectations. In ancient times, sailors argued whether the Earth was larger or smaller than estimates suggested, shaping voyages and ambitions. In the same way, the Hubble tension was more than a technical detail. It was a fault line across the map of the universe. Surveys responded with urgency. The SH0ES project, Supernovae H0 for the equation of state, pushed Cepheid and supernova measurements to new precision. The H0 collaboration used gravitationally lensed quasars as another ruler. Each pointed to the higher expansion rate. Meanwhile, Planck's results stood firm, and other cosmic microwave background analyses reinforced the lower rate. As more methods piled on, from tip of the red giant branch stars to water masers orbiting black holes, the cosmic jury remained split. The tension refused to vanish. It was not error, it was not noise, it was something deeper. And so the Hubble tension became not just a problem, but an opportunity. For in the cracks of contradiction, new physics might emerge. The maps, after all, are not simply for navigation, they are for discovery. If tomorrow, a breakthrough reconciled the two values, cosmologists would breathe relief. But if not, if the tension holds, it may point to truths we do not yet comprehend. Perhaps the universe is stranger, more layered, more dynamic than even our boldest theories predict. For now, the Hubble tension stands as a symbol. It tells us that even in an age of satellites and supercomputers, the cosmos resists full comprehension. It reminds us that science thrives not on certainty, but on mystery, and it proves that the map that changed everything is not finished. It still changes, line by line, number by number, with every new observation. The Hubble tension did more than unsettle equations, it rallied a generation. Across continents, observatories, and disciplines, the crisis became a beacon, calling scientists to action. If the map of the cosmos was fractured, then it would take a global effort to stitch it whole again. Collaboration is the lifeblood of modern astronomy. No single telescope, no single nation can map the universe alone. The Hubble tension underscored this truth with urgency. Teams from Europe, the Americas, Asia, and beyond began to weave their efforts together, sharing data, refining methods, and designing missions explicitly aimed at breaking the deadlock. At the heart of this response were the Great Sky Surveys. The Sloan Digital Sky Survey had already revolutionized our view of galaxies, charting millions of them across cosmic time. But the tension demanded more. Instruments like the Dark Energy Spectroscopic Instrument, DESI, rose to the challenge, targeting tens of millions of galaxies to measure their redshifts with exquisite accuracy. Each measurement was a thread, and together they wove a tapestry of the universe's expansion history. The Vera Rubin Observatory, once known as LSST, became another pillar. With its enormous 8.4-meter mirror and wide-field camera, it promised to scan the entire visible southern sky every few nights. The result would be a living map, tracking billions of galaxies, supernovae, and variable stars over time. Its data could illuminate whether local expansion rates were anomalous or whether the Hubble tension was baked into the very fabric of space-time. In space, new eyes joined the quest. The European Space Agency's Euclid mission, launched to study dark energy and dark matter, doubled as a probe of the Hubble constant. By mapping the subtle distortions of galaxy shapes through weak gravitational lensing, Euclid provided yet another ruler to measure cosmic expansion. Meanwhile, NASA's James Webb Space Telescope extended the cosmic distance ladder deeper than ever, observing Cepheids and supernovae with unprecedented clarity. And this was only the beginning. The Nancy Grace Roman Space Telescope, sometimes called Hubble's wide-eyed successor, was designed with dark energy and expansion in mind. With its immense field of view, it could capture thousands of supernovae across vast stretches of space, building an unparalleled dataset. These missions were not isolated. They were symphonies, coordinated in time and purpose. Data from one instrument fed into another. Calibrations crossed borders, and papers listed hundreds of authors from dozens of nations. The Hubble tension was no longer a puzzle for a few. It was a riddle for humanity itself. International workshops became crucibles of debate. Physicists argued passionately. Was the answer hidden in unknown systematics, or did it demand new physics? Some sessions resembled courtrooms, with evidence presented and rebuttals fired. Others resembled brainstorming sessions, where wild ideas like early dark energy or primordial relics were sketched on blackboards. The shared goal was not victory, but clarity. The crisis also reached students and the public. Articles and documentaries spread the story of the Hubble tension far beyond academia. It was a reminder that even in the 21st century, with satellites orbiting Earth and computers simulating galaxies, the universe still held secrets big enough to humble us. It became a cultural symbol, proof that science is alive, restless, and unfinished. There were moments of tension among scientists too. Competing teams defended their methods, journals debated priorities, and sometimes politics seeped into collaboration. But the greater vision prevailed. The map mattered more than ego. The Hubble tension, rather than dividing, ultimately unified. The effort brought with it a subtle shift in philosophy. For decades, cosmology had been a field of triumph, celebrated for precision and consensus. But the tension reminded scientists of the value of uncertainty. To admit we do not know is not weakness. It is the first step to discovery. By the end of the 2020s, petabytes of data flowed into servers, pipelines, and shared repositories. Maps were redrawn not once, but continuously, refined by each new observation. Slowly, patterns began to emerge. Some suggested that early dark energy, a brief exotic phase in the young universe, might reconcile the numbers. Others pointed to overlooked astrophysical complexities. Still others insisted that the cosmos was nudging us toward a paradigm shift. What was certain was this: the Hubble tension had ignited one of the greatest scientific collaborations of our age. Like sailors pooling maps to chart a dangerous sea, astronomers pooled their data to chart the cosmos. And in doing so, they reaffirmed that science is not just equations and instruments. It is a human endeavor, collective and shared. The map that changed everything was still unfinished, but thanks to these global efforts, It was being filled in faster, richer, and more beautifully than ever before. When the first wave of new missions returned their data, the astronomy community held its collective breath. Would the Hubble tension dissolve into a trivial mistake? Or would the contradiction grow sharper? The results did not smooth away the conflict, they deepened it. The map, once thought stable, now shimmered with possibility, forcing theorists to expand their imaginations. Among the first bold ideas to gain traction was early dark energy. In this scenario, the cosmos did not coast quietly after the Big Bang until dark energy's late rise. Instead, it briefly experienced a burst of repulsive energy in its youth. This would have altered how fast the universe expanded during its earliest centuries, slightly shifting the scale of the cosmic microwave background. That shift could reconcile Planck's 67 with the local 73. For years, early dark energy lingered on the edge of speculation, but as data poured in, it gained serious attention. Another frontier idea looked at extra particles, sometimes called dark radiation. The known universe is filled with photons and neutrinos, but what if other, light, fast-moving particles once roamed the cosmos? Their presence in the early universe would have accelerated expansion, again adjusting the cosmic microwave background's imprint. Physicists proposed sterile neutrinos, hypothetical cousins of ordinary neutrinos, or even more exotic species of matter. Still others turned to the very foundation, gravity itself. Einstein's general relativity had withstood a century of tests, from bending starlight during eclipses to guiding GPS satellites. But could it be incomplete? Modified gravity theories suggested that the force-binding galaxies might shift over vast timescales or in regions of extreme density. In such models, the equations themselves change subtly, altering how galaxies drift apart. The Hubble tension, in this view, was not a mistake, but a symptom of gravity's hidden complexity. Cosmologists also revisited dark energy's nature. Instead of a constant vacuum energy, perhaps it was dynamic, a field that waxed and waned. If it grew stronger, earlier than expected, it could alter the entire expansion history. Some proposed phantom energy, which grows with time and may even tear the universe apart in a big rip. Others offered smoother, evolving fields that might bridge the gap between local and cosmic measurements. Each theory carried risks. They were elegant but untested, and worse, they risked violating the very successes of the standard cosmological model, which explained so much so well. Any new proposal had to walk a razor's edge, solving the tension without breaking the rest of the cosmic map. This challenge turned the community into a crucible of creativity. Papers flooded Archive, conferences buzzed with presentations, and simulations ran on supercomputers across the globe. Early dark energy models were refined, then stress-tested. Modified gravity theories were stretched to extremes. Dark radiation candidates were compared against particle accelerator data. Theories rose and fell with each new release of survey results. The James Webb Space Telescope played a pivotal role. By observing Cepheids and Type Ia supernovae with unmatched resolution, it slashed uncertainties in the local ladder. If systematics had plagued earlier data, Webb would reveal them. Instead, it confirmed the high expansion rate. On the cosmic, microwave background side, Planck's results were checked by South Pole telescopes and Atacama observatories. Their measurements echoed Planck, standing firm on the lower rate. The contradiction would not vanish, and so more radical possibilities emerged. Some cosmologists speculated about a multiverse influence, subtle interactions between our universe and hidden neighbors. Others considered the idea that our local region of space is unrepresentative, that we live in a Hubble bubble, a cosmic neighborhood expanding differently from the average. But simulations showed such a bubble could not account for the full tension. As wild as these theories sounded, they were not dismissed outright. History had taught humility. Dark matter, dark energy, and cosmic inflation had all once seemed like fantastical intrusions before becoming pillars of modern cosmology. Perhaps the Hubble tension was the next door waiting to be opened. What was clear was that the tension had become a playground for bold ideas. The cosmic map was no longer a single chart with neat labels. It was a canvas, and physicists painted it with hypotheses as varied as their imaginations. Some strokes would fade, others endure, but all carried the same spirit, a refusal to let contradictions stand unanswered. The story of science has always been one of tension transformed into progress. The orbit of Mercury once defied Newton, and from that crack emerged Einstein's relativity. Today, the expansion of the universe defies consensus. From this rift may emerge the next great revolution. For now, we live in the midst of uncertainty, a thrilling and unnerving state. The numbers 67 and 73, repeated in papers and debates, are no longer mere values. They are symbols of mystery. They remind us that the universe is not a solved puzzle, but a living riddle. And in seeking its answer, we reshape the map that changed everything. Theorists had drawn their bold sketches. Early dark energy, exotic particles, evolving dark energy, modified gravity. But sketches are fragile things. To endure, they must be tested, measured against reality, dissected by data, challenged until only the strongest survive. Section 13 is the story of how humanity set about testing the universe itself, turning imagination into experiment. The first arena was the realm of supercomputer simulations. Cosmologists built digital universes, coding in equations of early fall, dark energy or altered gravity. Billions of virtual galaxies evolved under different rules, each simulation a mirror held up to reality. Teams compared these synthetic maps with the vast catalogues from Sloan, Deci, and Rubin. Did the clustering of galaxies, the shapes of voids, the alignments of filaments agree with theory? Sometimes yes, often no. Each failure was precious. It narrowed the possibilities, carving away fantasy until only viable models remained. Next came the rising power of gravitational waves. First detected in 2015, ripples in spacetime offered a brand new cosmic ruler. When neutron stars collided, they released gravitational waves and flashes of light. By measuring both, astronomers could compute distances directly, independent of Cepheids or supernovae. These standard sirens became a third ladder, neither local nor cosmic microwave background, but something in between. Already, early measurements hinted at expansion rates consistent with the higher 73, but the uncertainties were wide. As detectors multiplied, from LIGO to Virgo, from CAGRA to the planned Einstein telescope, astronomers saw the dawn of a future where hundreds of such sirens might weigh in on the Hubble debate. Meanwhile, cosmic microwave background experiments continued to refine their vision. The South Pole Telescope and Atacama Cosmology Telescope probed the faint polarization patterns of relic radiation, squeezing every ounce of information from the infant cosmos. If early dark energy had left its fingerprint, these instruments would catch it. Some datasets showed tantalizing hints, a slight preference for models with an extra kick of energy. Others were inconclusive. The cosmos seemed to whisper without speaking clearly. On the particle frontier, experiments sought evidence of sterile neutrinos or other exotic particles. Deep underground detectors, shielded from cosmic rays, listened for faint signals. AME, CERN and Fermilab, accelerators searched for deviations in neutrino oscillations that might point to hidden species. Every null result closed one door, but sharpened the search for another. Astronomers also turned to weak gravitational lensing, the subtle warping of galaxy shapes by invisible matter. If gravity itself behaved differently on large scales, lensing, patterns would reveal it. Euclid's sweeping survey became a crucial testbed, mapping distortions across billions of light years. Its images, combined with Rubin's time domain data, offered a new perspective on the cosmic scaffolding. Amid this flood of tests, the community wrestled with a paradox. Each new dataset confirmed the tension, but none clearly resolved it. The key contradictions were real, but the solutions remained elusive. Conferences were filled with cautious excitement, as though the field stood on the threshold of something vast. For young scientists, the tension was an invitation. Doctoral students and postdocs staked their careers on models once considered fringe. Early career astronomers, unburdened by the weight of consensus, tested daring combinations. Hybrid models of evolving dark energy plus exotic particles. Simulations blending modified gravity with dark matter physics. A sense of intellectual renaissance spread, not unlike the flowering of cosmology after the discovery of cosmic acceleration in the 1990s. Public interest also surged. Documentaries explained standard sirens to global audiences, portraying colliding neutron stars as lighthouses flashing across space-time. Headlines framed the Hubble tension as the universe's greatest unsolved riddle. Popular science magazines illustrated cosmic maps with diverging paths, one at 67, one at 73, arrows pointing to new physics ahead. But behind the fascination lay an undercurrent of humility. Every experiment had limits. Gravitational waves were still rare. Particle physics was constrained by budgets. Telescopes faced weather, funding, and politics. Scientists could not command the cosmos to reveal itself. They could only wait, observe, and refine. And so the tests continued. Year by year, error bars shrank, simulations grew sharper, collaborations expanded. Slowly, a picture began to form. Early dark energy models remained on the table, but the simplest versions were ruled out. Modified gravity faced steep challenges, its predictions clashing with lensing data. Dark radiation grew less plausible, hemmed in by both cosmology and particle physics. Theories fell away like leaves in autumn. What remained were subtler, more intricate ideas. Early dark energy that faded quickly, evolving dark energy with finely tuned behaviors, hybrid models requiring patience to evaluate. The cosmic map had not yet revealed its final contours, but the outlines were sharpening. And through it all, the Hubble tension persisted, a reminder that discovery is not instant, but iterative. Each test was not an end, but a step in a grand relay. One team passed the baton of knowledge to another, across continents, across generations. Together, they were chasing the truth of the universe, knowing it might take decades to catch. The map that changed everything was still in flux, but with every simulation, every siren, every data set, humanity moved closer to seeing the universe not as fractured, but whole. Science is often portrayed as a march towards certainty, a linear path where confusion is gradually replaced by clarity. Yet the story of the Hubble tension revealed something more profound, that knowledge itself is provisional, that mystery is not a weakness, but the very lifeblood of discovery. By the time the contradiction between 67 and 73 had weathered years of tests, it no longer felt like a simple measurement dispute. It became a mirror reflecting how humanity thinks about truth. Astronomers were forced to admit, publicly and humbly, that the universe was stranger than expected. This humility resonated beyond labs and observatories. To the layperson, the idea that scientists, so often depicted as authority figures wielding definitive answers, could disagree so fundamentally was both unsettling and inspiring. Students encountered the Hubble tension in textbooks and realized that science was alive, unfinished, and open to their contributions. Teachers used it to show that learning is not memorization of facts, but participation in a dialogue that stretches across centuries. Philosophers found in the tension a case study in epistemology. How do we know what we claim to know? If two impeccable methods gave contradictory answers, was knowledge dependent on perspective? Was truth a single mountain peak with many paths, or a range of peaks, some hidden behind clouds? The debate echoed ancient questions about certainty and doubt. Historians of science drew parallels. The orbit of Mercury had once defied Newtonian mechanics, forcing physicists to invent hypotheses until Einstein's relativity revealed a deeper truth. The ultraviolet catastrophe of the 19th century had required quantum mechanics to resolve. Again and again, progress had been born not from harmony, but from tension. The Hubble conflict seemed to follow the same arc: contradiction as prelude to revolution. Culturally, the Hubble tension seeped into art, literature, even music. Poets wrote verses about numbers that did not agree, likening them to lovers speaking past each other. Musicians composed symphonies where themes clashed and overlapped, echoing the discord of expansion rates. Painters depicted fractured cosmic maps, galaxies tugged in different directions, beauty born of imbalance. The universe, once thought silent, was suddenly a chorus of competing voices. Even within the scientific community, the tension fostered new virtues: patience, openness, collaboration. The old model of lone geniuses making grand proclamations gave way to vast teams, sharing data across continents, uniting radio telescopes in Chile with gravitational wave detectors in Italy, linking supercomputers in the US with satellites orbiting Earth. Knowledge was no longer a possession, but a collective act. And for the public, the contradiction had an unexpected side effect: wonder. Far from undermining trust in science, the acknowledgement of uncertainty humanized it. People saw not cold certainty but genuine curiosity. They recognized themselves in scientists' confusion, and that recognition forged connection. There was also a spiritual dimension. For millennia, humans looked to the heavens for stability. The stars rose and set predictably. The constellations endured. But the Hubble tension whispered that even on the grandest scales, certainty could dissolve. Some found this unsettling. Others found it liberating. If the cosmos itself carried mysteries, then perhaps mystery was not an obstacle to be conquered, but a companion to be embraced. At night, when telescopes tracked Cepheids or gravitational waves rippled invisibly through Earth, countless ordinary people read articles or watch documentaries about the debate. Many drifted into sleep, pondering not only galaxies, but the very nature of knowledge. What does it mean to know? What does it mean to live in a universe where even experts admit they do not yet understand? The cosmic map had changed everything, not because it revealed final answers, but because it showed the beauty of questions. By section 14 of this saga, the Hubble tension had transcended science. It had become metaphor. It symbolized doubt, progress, humility, and the unending search. It reminded humanity that every time we chart the universe, the chart is provisional, a draft subject to revision. And in that draft, in those revisions, lies the poetry of existence. The final chapters of the story would not simply be about numbers, but about what those numbers meant for humanity's place in the cosmos. The contradiction, persistent and unresolved, had given us more than a puzzle. It had given us perspective. The story of the cosmic map began with numbers, with the innocent-seeming act of measuring how fast the universe expands. It might have ended there, with a quiet agreement on a value and a neat entry in a textbook. But instead, it became something far greater. A journey into uncertainty, a reminder that knowledge is fragile, that truth is layered, and that mystery is eternal. By now, the debate between 67 and 73 has echoed across years, experiments, telescopes, and generations of thinkers. The tension has not resolved fully, though progress continues. Perhaps in the next decade, gravitational wave sirens will settle the question. Perhaps subtle new physics will emerge, revealing truths we have not imagined. Or perhaps the contradiction will endure, a cosmic riddle left to future centuries. But even if the resolution lies beyond us, the journey itself has changed us. Science thrives not because it delivers perfect answers, but because it dares to ask imperfect questions. The Hubble tension reminded us that certainty is not the default state of the universe. The cosmos does not owe us clarity. It only offers patterns, traces, and whispers. Our task is to listen carefully, to measure patiently, to imagine boldly, and to accept with humility that our maps are sketches, not final drafts. Look back at the arc of this narrative. We began with Edwin Hubble himself, shocked to find that galaxies were receding, that the universe was expanding. His discovery overturned centuries of static models. Then came the great observatories, from Hubble Space Telescope to Gaia, from Planck to Euclid, each layering more detail onto the map. And then, just when it seemed we had achieved precision, contradiction emerged, numbers diverged, certainty dissolved, mystery returned. But perhaps this is the truest rhythm of science: discovery, confidence, contradiction, renewal. Like waves against a shore, knowledge advances not smoothly, but in surges and retreats. What endures is not the correctness of a single number, but the courage of a species willing to look upward and ask. The cosmic map, fractured though it seems, is a testament to human unity. To create it, thousands of people across cultures and nations collaborated. Engineers building instruments, scientists analyzing data, students learning to code simulations, artists translating concepts into visions. Together they painted the largest canvas humanity has ever attempted, the universe itself. And though the map remains incomplete, it is already magnificent. Galaxies cluster, filaments stretch like threads of light, voids yawn with quiet grandeur. Whether the expansion rate is 67 or 73, the universe remains a vast and humbling home. For those listening tonight, perhaps curled beneath blankets or gazing out of a window into the dark, let this story be a reminder. Mystery is not our enemy, it is our companion. It gives us reason to keep exploring, to keep learning, to keep imagining futures where knowledge expands like the cosmos itself. When you drift into sleep tonight, remember that you are part of this story. Your curiosity, your willingness to listen, your support for journeys like this, they matter. Every subscribe, every like, every share is not just a gesture. It is the quiet fuel that lets these explorations continue. It is the encouragement that keeps these late-night stories alive, weaving together a small but beautiful community of dreamers scattered across the world. So thank you for being here. Thank you for listening. And if you have not already, I invite you to join this circle of curiosity. Subscribe, like, and follow along. Not because algorithms demand it, but because together we are building something rare. A shared space of calm wonder in a noisy universe. The cosmic map that changed everything is still unfinished. But then, so are we. Perhaps that is the greatest beauty of all. Good night, and may your dreams carry you far among the stars.